right, how's it going, everybody? I am here on Friday, April 30th, and today we're going to look at our very last section of the semester, section 11.10, Taylor and Maclaurin series. Um, this is a good one. I love the fact that we get to wrap up with this topic because this is both really, really interesting, it's relatively simple, and it's massively useful. So this is like a really, I don't know, it's a good ending topic because no matter which way you care about this, like this is an awesome topic right here. So in the last video, we were looking at power series, and what we found was that we were able to identify power series associated with functions that were in some sense nearby to the form of the value of a convergent geometric series, our a over 1 minus r, right? And so if we were algebraically nearby to that with the function that we wanted to estimate with a power series, then we could manipulate it a little bit, force it to get the rest of the way into that a over 1 minus r format, and then identify its series. Alternatively, we saw that we could also sometimes use derivatives and integrals to sort of coerce our function to look more like the a over 1 minus r format, determine the series, then maybe undo some derivatives or integrals to return back to a series representation for the function of interest. That was really limited, though, because it was highly dependent on our ability to get into this a over 1 minus r structure, which we're certainly not going to be able to do for all functions. Think about things like e to the x, sine of x. These are just functions where we're just never going to get them into rational form like that, and no derivatives or integrals are going to get us near to their rational form. It's going to look like that. So what we want to do today is we want to generalize what we did in the last video so that this works for any differentiable function rather than just ones that are either by way of algebra or calculus nearby to a over 1 minus r. The really good news here is that we can derive this formula for the power series of a general function by just taking some pretty generic derivatives here. So we're not going to, like, this is going to be honestly a very simple derivation of a formula here that is wildly useful and is going to encompass not only everything we did in the last video, but tons of other functions as well. So we're going to start by saying, suppose that our function of interest, so f of x is the function that we are attempting to come up with a series representation for. We're going to just assume that it has some power series representation, so it's just got some generic coefficients out there, c sub n's, and we know that our power series could be centered at any x location, making our estimate, remember, we're making an estimate that may only be good for an interval. We get to choose where we would like that interval of goodness for estimation to be centered, and it's going to be centered at the value of x equals a. So that's why that shift is always generically in there. We'll talk about when we include that and when we don't in one moment here. It's really just a definition thing. In that case, you can see that this is just what our generic power series looks like all written out, right? There's all of our c sub n's. There's the x minus a's to their integer powers. This is just us writing out some terms of a super generic series right here. So the point is this. If we could determine what all of these c sub n values are going to be right here, then we straight up know the power series representation for f of x. That's not the stuff that I'm worried about, or that's the stuff I'm worried about finding. The x minus a to the n is always just going to look like x minus a to the n in the power series representation. It's the c sub n's. We're saying, what are those for any given function, right? So the point is, if we could determine all the c sub n's for a particular function, then we would know the power series that represents it. That's it. That's all we have to know. We just have to determine these coefficients c sub n's. Fortunately for us, there's only an infinite number of the c sub n, so if we can just one by one determine all infinite number of them, then we've got them all. So let's get started right here. So this is going to be a cool and easy derivation right here for such a big and powerful idea. I really, really like this. So let's go ahead and derive the formula for a general Taylor series here. So we're starting just with some super generic representation. So again, this f of x right here, that might be our e to the x, our sine of x, our tangent inverse of x, anything else we want it to be. And we think that there is this infinite series representation. Very important that those dot dot dots are on the end right there. It is an infinite series. And so what we want to do is just what we saw happen graphically in the last video. I want to make sure that this estimating function, the series that is estimating the actual function of interest, it should match the function value at the center of the estimate. It should match the first derivative. It should match the second derivative, right? So we're going to end up matching a bunch of derivatives between our function of interest and determining what coefficients will guarantee that we match that the all of the derivatives at that one location where the estimate is centered. So all we're going to do here, I'm going to describe to you what our process is going to be because it's really simple, and then we'll just go ahead and do several steps of it. All this process is going to look like is this. We're going to plug in a for x, and we're going to determine a coefficient. Then we're going to take a derivative of both sides of the equation that you're seeing right here. Then we're going to plug in a, and we're going to determine a coefficient. Then we're going to take another derivative, plug in a, determine another coefficient. That's all we're going to do. Plug in a to determine a coefficient, take a derivative. Plug in a to determine a coefficient, take a derivative. We're just going to do that enough times that we've seen a pattern and then identify the pattern that we've seen. So let's go ahead and do it here. So the first one, I'm going to go ahead and plug in a. Notice when I plug in a in for x, x minus a becomes 0 for every single term in the series except for 1. So it looks like c sub 0, and remember our goal is to identify all of the c sub n terms. We just found the first one. It looks like your constant coefficient on any of your Taylor series, your general series representing a function, should just be the function value evaluated at the center of the estimate, where we're centering our estimate at right here. So I'm going to go ahead and kind of highlight that one right there and say that one was easy. Now we're going to go ahead and we're going to take a derivative of this function on both sides, right? So now when I take this derivative, now f prime of x, the constant goes to 0. You should notice that here, this is really c1 times x minus c1 times a. But c1 times a is just a constant, so the derivative of that goes to 0. All we really need to worry about is taking the derivative of c1 times x, which is just going to leave us with c1, plus the 2 is going to come down in front, so we're going to get a 2c2 times x minus a, now to the first. I'll just write that to the first right there. Plus, we're going to get a 3c3 times x minus a squared, plus 4c4 times x minus a cubed, plus, and that's as far as we're going to go. We're going to find all the way, we're going to find c0 through c4, like actually find them, and then we'll identify our pattern from there. So now, as promised, now that we've taken a derivative, let's go ahead and evaluate this derivative at a. And if we evaluate this derivative at a, what you should notice, again, is that all of the terms that have an x minus a just went to 0. The only one that didn't is c1. So it looks like c1 is just the first derivative of the function evaluated at the location at which we are centering the approximation. Now let's go ahead and take another derivative. Wait, I gotta say how easy that was again. Now let's take another derivative. Now f double prime of x, so c1 has gone to 0. 2c2 times negative a, all a constant, that goes to 0. But 2c2 times x, I can take the derivative of that, and I'm going to get 2c2. What are we going to get over here? Plus, it looks like the 2 is going to come down and join up with the 3 to give us 6c3 times x minus a to the first. Plus, the 3 is going to come down and join the 4 to give us a 12c4 times x minus a squared. And we're only going to go out that far, so I'm just going to keep on not indicating any terms beyond that one right here. But the good news is that now it's pretty easy for us once again to go ahead and plug in a, let almost everything go to 0, right? This term's 0, this term's 0, all other terms are 0 because when x is equal to a, we get 0 in the parentheses. But 2c2 seems to have survived. Remember that our goal is to find all of these constants, the c sub n's. So the last baby algebra step I want to do is just divide both sides by 2 here. So it looks like we're getting f double prime of a over 2 is equal to c2. Still easy. Let's go ahead and identify that one. So we've done the first 3 out of the infinite number that we need. All we want to do is start recognizing that there should be some pattern that we should be recognizing emerging here. So let's do it again. Now we've got f triple prime of x. And what are we going to get? Well, the 2c2 is a constant, so that goes to 0. It looks like 6c3 is what we're going to get for the derivative of our second term. Over here, it looks like when we take this derivative, the 2 is going to pop down and join the 12, and it's going to give us, therefore, a 24 c4 times x minus a, only to the 1 power now. And then all the other terms that are out there that we know are out there, but we're just not here identifying. And when I go ahead and I check out f triple prime at a, well, we can clearly see we're just getting 6c3. And therefore, it clearly looks like f triple prime of a over 6 is going to be c3, right? So we can just do this forever, but what we really want to know is what is c sub n going to be, right? Now, what I think that we can also see right here, now that you're starting to see this pattern, we saw here that this 2c2 resulted in 2 being the denominator under the second derivative. 6c3 said that 6 was going to be the denominator underneath the derivative. It looks like 24 is the next one up right here. So it also looks like we're seeing here, I think that I can say f, the fourth derivative of f at a over 24 seems to be what c4 is going to have to be. And so my question to you is, what is this pattern that we're seeing? Well, the denominators for n and the denominator. Just make a tiny table right here so we can see what happened. When n was equal to 0, n is 0, c sub n, c sub 0, the denominator underneath underneath f of a was just 1, right? And then also, when we looked at c1, the denominator under f prime of a was also just 1. But then when we bumped up to c sub 2, the denominator under the second derivative was 2. Then when I stepped up to 3, the denominator underneath c sub 3's expression here was a 6. And then when we did c sub 4, we got 24 as our denominator. So I'm asking you, what function gives us these terms right here? And the answer is, we can see how these were constructed. And what I want you to stop and think about right now is, how did we get to 24? Where did the 24 come from? 24 was really 2 times 12, which was really 3 times 4. So it looks like how we got to 24 was 2 times 3 times 4. So that sounds to me a lot like a factorial. And in fact, what we're going to see here is that this is equal to n factorial, because 0 factorial is 1, 1 factorial is 1, 2 factorial is 2 times 1, which is 2, 3 factorial is 6, because it's 3 times 2 times 1, 4 factorial is 24, because it's 4 times 3 times 2 times 1. So it seems like because the derivatives are going to continually pop down the next integer to multiply by, or I should say that one reduced integer to multiply by, we're always going to get integer factorials underneath the appropriately ordered derivative. The nth derivative at a divided by n factorial is always going to be our c sub n term. And remember, that's literally all we needed to know. I literally know how to make the Taylor, the power series representing any function at all now, because we just identified what all of the c sub n's are always going to have to be. It's always going to be the nth derivative evaluated at a divided by n factorial. That's c sub n in all cases. This was a general version right here. So we can see this pattern right here. This is me just stating exactly what we just said right here, that all these coefficient terms are going to be the nth derivative evaluated at a divided by n factorial. That this is what gives us our general definition of a Taylor series. This is our c sub n right here. Oh, I'm sitting inside of a, there we go. This is our c sub n term right there that we just identified by a little bit of visual inspection right there, times the power series terms that we always get, x minus a to the n. It's very, very, very typical. I'd say by far the most common Taylor series that you encounter in general in the wild are centered at 0 often, so that a term being 0. The special case of a Taylor series centered at 0 is called a Maclaurin series. There's no distinction between them. A Maclaurin series is just a special case of a Taylor series. So If someone says evaluate the Maclaurin series, they don't need to tell you where it's centered. It's automatically centered at 0. If someone says evaluate the Taylor series of this function centered at x equals 0, they really mean evaluate the Maclaurin series. That's just a naming thing right there. There's nothing really special about that distinction. This is just a special case of a general Taylor series. So Taylor is the general case. Maclaurin series is the special case where we're centered at 0. So let's look at a few Taylor and Maclaurin series and their uses. So importantly today, we want to build a couple, but I also want to convince you why it matters that we can do this. And I'm going to show you some really cool problems that we can solve now that you could have never solved, or I shouldn't say solve, I should say at least estimate solutions to, but that's also, I mean, what really happens in most practical math anyway. It's also the case that in your homework, you're going to see a lot of work with these things here. So I sort of picked my examples based on avoiding what I know that you're going to end up doing in the homework, which is why we're going to end up, well, okay, let's just go ahead and do the examples we're going to see here. You'll see the stuff in the homework you're going to see. So what I want to do is let's do some e to the x exploration here. Let's find a Maclaurin series for e to the x. I want to determine its interval of convergence. That's a really important thing here. The interval of convergence here is almost the most exciting part about all three parts of this example here. Doing that, I want to know, can you come up with a series that represents the numbers e and e squared? Then let's also look at an example where we are not centering our estimate at x equals 0. Let's instead center our estimate at x equals 2. And again, we want to, just like in the last video, I want to go to Desmos for like all this stuff to make sure that we can see the graph, see a little bit of the computation for the estimates that we're making, stuff like that. So let's go ahead and do it. So for e to the x, what I know that I'm doing is I want to come up with the Taylor series. Let me get back in colors here. I want to come up with the Taylor series. I'll just call this t sub n of x right now for e to the x should be the series from n equals 0 to infinity of the nth derivative of the function evaluated at a divided by n factorial times x minus a. So in this case, we have that, so I'm going to say a here. So we have that the Maclaurin series says to us that a is going to be equal to 0. That's where we're centering our Taylor series at, our series estimate of the e to the x function. And the other thing that's really, really nice that we know about e to the x, what makes e to the x one of the most special functions in all of calculus, is that it's the only function that it is its own derivative infinitely many times, right? So the nice thing about e to the x is that when f of x is equal to e to the x, what I know is that the nth derivative of x is also e to the x. This is really, really special right here. It's the only function for which you're just going to be able to say, oh, and this is what it always is right there. This is rare, incredibly rare that you get to do this in this case, but e to the x it's just a special function like that. So I think that I can kind of put some of this stuff together here. The only other thing that I want to then say is we're going to be evaluating this guy at 0. And so you should notice to yourself that that means to me that we are looking at f, the nth derivative of f evaluated at 0 is going to be e to the 0, which is just 1 in this case, right? So what I'm thinking is it should be the case that e to the x is equal to the series from n equals 0 to infinity of just 1 over n factorial. Oops, by the way, I missed my nth power right there. Times, and that's x minus 0. And that seems to be it. It seems like this is our representation for e to the x. Let's write out a few terms so we can visually get a sense of what this function looks like. When n starts at 0, remember that 0 factorial is 1. That's not just like a byte. That's like actually how you evaluate 0 factorial. So we're going to get 1 times x to the 0, which is also 1. So I'm just going to get 1 plus. When n is 1, we're going to get 1 x to the 1, so I'm just getting x. When n is 2, I'm going to get 1 over 2 factorial times x squared. So I'm going to get x squared over 2 factorial. And we're just going to keep on getting terms that look like this. So it looks to me like the claim is that this is a series that represents the function e to the x right here. The question is, what what interval over which does it actually converge to this, right? And I feel like I kind of want to put like a little bit of a question mark right there. Like, I don't want to say that those two functions are straight up equal to one another if I really mean that e to the x is only the same thing as that series, like in negative 1 to 1 or something like that. And the whole last video that we saw, all of our intervals of convergence were only from negative 1 to 1, except for the one example that was negative 5 to 5. But that really meant that we shouldn't just say that the function equals the series straight up if it's only true that they're equal over some interval over which that series does converge on that value. So let's go ahead and look at the interval of convergence to decide how legit is that equals sign right here. So our question is, what is the interval of convergence of this thing right here? So let's look at our convergence. As we did many times in the previous video, let's look at the ratio test here. I would think the ratio test is good because I have powers and factorials. That's all sorts of multiplication. Right? So we want to see that it converges when the limit of consecutive, the absolute value of consecutive terms as n goes to infinity is less than 1. So if I do that in this case right here, you should be seeing that we are going to be getting, it looks like here, the limit as n goes to infinity of the absolute value of, it looks like I'm getting x to the n plus 1 over n plus 1 factorial, all divided by x to the n over n factorial. So we're going to, make our fraction actually readable here and write this as limit as n goes to infinity of, let's see here, we're going to flip these up. So we're going to get x to the n plus 1 and just regular old n factorial there. In the denominator, we're going to get the x to the n, and we're going to get the n plus 1 factorial. And really nicely here, you should notice that this is just going to leave us with an x on top. It's just going to leave us with an n plus 1 on bottom. And the question that I have for you is this. For what values of x is this limit less than 1? Notice that in this limit, n is going to infinity, but x is technically a selected constant by us, right? So n is getting infinitely large, so this limit is going to go to 0 always. So let me write this slightly differently. I think I just want to say this is straight up equal to 0, which is less than 1 for all x. So this power series, power slash Taylor slash Maclaurin series, any of those names would be acceptable. So that is exciting right there. That is an exclamation mark of excitement, not of factorial. Literally, it will actually be straight up equal to that function at all x values. That is super, super cool right here. So I kind of want to see this thing in Desmos if that's actually going to be true here. So let's go pop over to Desmos and see this slightly unbelievable statement, which is that we literally just figured out a way to write e to the x as a polynomial, which is, I mean, that's blasphemous right there, right? I mean, it's an exponential function. It doesn't have a way to be represented by a polynomial, but this is just our 1000th lesson this semester that says, hey, listen, man, infinity can do weird stuff to you right here. And if we have an infinite number of terms, then these functions are just straight up equal to one another. So let's go ahead and let's take a look over at Desmos here, what we're going to end up seeing. And so our graphical scenario here is going to look a lot like the one from the previous video. However, what you should be expecting to see, and I want to like set you up for this right now. Remember in the previous video, all the series that we came up with that were estimating a function, they only were a good match for that function. Almost all of them were just from negative 1 to 1, and elsewhere they just diverged away. What we're claiming here is that as we tack on more and more and more terms, it's just going to keep agreeing over a wider and wider span with that e to the x function. And if we have an an infinite number of terms, then it is just straight up the same thing as e to the x, right? So we first are going to graph y equals e to the x. That's the function that we are estimating with the series that we just built. Then we're going to do y equals the sum from n equals 0, and we'll go up to a so that we can watch it kind of get built of. And what were the terms that we just came up with? I think we came up with x to the n divided by n factorial. And let's go ahead and add a slider for a. I want this to go from 0 to, I don't know, let's go 20 terms out and go by 1. And let's go ahead and watch this thing. So first things first, remember that our first term of our Taylor series should always just be the function value of the estimated function at 0 if we're estimating at 0, right? If we're centered at 0. So it always should be the case that the best point estimate of a function is literally that function's value. Since we're centered at x equals 0, we literally got the same value. Our first order Taylor approximation should always just be the best linear approximation of the function. So we're always just going to get the tangent line right there. Now you should notice this function is overall not doing a super good job of looking like e to the x, but that's because we only have the constant term and the linear term. Then we add in the quadratic term and it starts to look a little bit better. And then the cubic, and then the quartic, and the quintic. Now, here's the important thing. In the last video, again, we saw over here that this stopped agreeing around -1 on the left-hand side for like all the ones that we saw. What we're going to see in this case is that it's just going to keep on agreeing more and more and more further out. Oh yeah, oh yeah, oh yeah. It doesn't seem to be like we're reaching any point where it just says, oh, listen, we can't estimate this any better. We're just going to diverge away. The more terms we include, the wider of an interval over which this is an excellent, excellent estimate right here. And again, I know it looks like these curves are laying exactly on top of one another. They're not quite. There is ever so slightly some tiny, 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 tiny differences in these things right here. But you can see that those differences are outrageously small. I mean, as I'm zooming in here, we still can't see any amount of red line on the screen right here. I mean, this thing is pretty much nailing it right there. So what we can see is the more terms we include. All right, I'm going to go ahead and just make my Desmos freak out here. But yeah, look at this. If we go to 50 terms out, it looks like we're going all the way almost out to negative 19 now, all the way up to now. I guess it's going to be awful hard for me to visually investigate the right-hand side of this over here since it grows so quickly. But again, we're seeing something a little different than the last video, which is that this isn't just getting better out to -1 to 1 and then just never actually like breaking over that boundary. Every time we include more terms, it's stretching how far out we can go away from x equals 0 and still have a good estimate. And so I hope that you can imagine that if we go infinitely far out, then this is just going to match infinitely far out right there. So this is just going to straight up be the same thing as e to the x, regardless of what x value you plug in, as long as you're taking all of the infinite number of terms that are in the series, as opposed to just this finite series that we keep on exploring here in Desmos. Right? Very, very cool. So I just want to conclude here in Microsoft Word. I just want to say, so e to the x is straight up equal to the series n equals 0 to infinity of x to the n over n factorial for all x. That's crazy. And that's officially crazy, which is why I'm writing it in my notes right here, right? Those are literally equal to each other for all values of x. We made some estimates in the last video where we kind of said that. We said, oh, but it's actually only going to actually converge on that function in the interval -1 to 1 or something like that. Not the case here. Converges straight up everywhere. So that was our part A right there, is that we found the Maclaurin series for e to the x, Maclaurin meaning the Taylor series centered at 0. And we determined its interval of convergence, which was the entire real number line, negative to positive infinity. Let's use this information now to come up with ways that we can find series representations for some constants like e and e squared. So e to the x, as we wrote out a minute ago, is going to look like 1 plus x squared over 2 factorial plus x cubed over 3 factorial. Right. So it looks like now, for that part B question, we were interested in knowing what's a series representation for E. Well, E is just what you get when you plug in 1, right? So you should notice that this should really just be 1 over n factorial. as the series representation. Okay, I want to back that up so I can get these like aligned with each other here. Um, So we are plugging in x equals 1 to get e, right? So 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial. So we're claiming that the value of e is just straight up what that sum is going to be right there. So once again, let's just pop over here and convince ourselves that that is actually going to be correct. I can type in the number e right there, and we did 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial, and you should be seeing that we are certainly converging on the number that's going to look like e here. We could do one more, uh, 1 over 5 factorial right there. We're getting even closer, right? So it looks like this is a series of rational numbers that when summed together gives us an irrational number right here, which is super cool. And we could do the same thing for e squared. E squared, well, that should just be, now it looks like we're letting x be 2. So it looks like this is just going to be the sum from n equals 0 to infinity of 2 to the n over n factorial. So it looks like we're going to be getting instead, right? And again, I'm just literally, oh, sorry, got to pop over to Word right here. So we're looking at e squared right here. It's going to be the sum from n equals 0 to infinity of, and right here I've got 2 to the n instead of 1 to the n like in our previous example right there. And so here I can see that I'm going to get, when I plug in n equals 0, I'm going to get 1. When I plug in n equals 1, I'm going to get 2 because it's 2 over 1. When I plug in n equals 3, I am going to get, or sorry, n equals 2, and I'm noticing we're just right up here. I'm going to get 4 over 2 factorial plus 8 over 3 factorial plus 16 over 4 factorial. So what is that? 1 plus 2 plus 2 plus 3 factorial is 6, so 8 over 6. 4 factorial is 24, so 16 over 24. And once again, we can go to Desmos and ask ourselves, what's up with the series right here? Does this actually look like we're actually converging on e squared right here? And if we come on over to Desmos, then we can do the same thing that we just did. We got e squared now is what we're estimating. And we got 1 plus 2 plus 4 over 2 plus 8, 16, 32. And you can see, yeah, it looks like it's taking us a little bit longer maybe to get there for e squared, but we are certainly getting closer and closer and closer to that value associated with e squared as we introduce more and more and more terms that are on this thing right here. So again, really cool coming up with a series of rational numbers that converge on a known irrational number out here. Very exciting. So we have found series representations for e and for e squared. And again, I just think that this is just like a crazy statement right here, that this is like literally an alternate way to write the number e right there. The number e is the infinite series of the 1 over n factorials from n equals 0 to infinity. That's straight up equality. That's not an estimate. Those are literally the same number right there. And that's just wild to me that there's a way to write these things as integer-based fractions to get to, you know, our irrational numbers like e out there. So super cool. So that was our question B. So we found the Maclaurin series. We used the Maclaurin series to find a series representation for some constants, e and e squared, that are obviously, you know, e, one of the most needed numbers in all of mathematics. And so finally, let's go ahead and find the best quadratic approximation to e to the x centered at x equals 2. So our couple things here are this. One, we're now going to make a new series formulation where we're centered at x equals 2. So a is going to be 2 in this formula rather than a being 0. The other thing is that we are only interested in a quadratic approximation to e to the x. What that means to me is I'm only interested in going up until I hit my x squared term, and then I'm going to stop. And I'm going to claim that if I wanted to come up with a quadratic that represents e to the x, but is a good estimate near x equals 2, rather than near x equals 0, this would be the best possible quadratic to use to make that type of estimate. All right? So let's go ahead and see if we can do this guy here. So we want to come up with our Taylor for e to the x at x equals 2. Now, in this case, however, we are centering our approximation at x equals 2. So I want to identify that the nth derivative evaluated at 2 is going to be e squared. All right? So what that means to me is that when I go to build my Taylor series, which I'm going to call t sub 2 of x, that this should be the sum from n equals 0 to 2, because I only want to build a second order polynomial. And that is going to be of our the nth derivative evaluated at 2 over n factorial times x minus 2 to the n. What are we going to end up getting here? Well, it looks like it's going to be e squared is this constant on top always. But e squared is just a constant over n factorial times x minus 2 to the n. So what are we going to get here? When n is equal to 0, this term is 1, the n factorial is 1, and so we're just going to get e squared. When n is equal to 1, n factorial is still just 1, but now we're going to get one copy of x minus 2, so it seems like we're going to get plus e squared times x minus 2. And finally, when n is 2, we are going to get that n factorial is 2, so I'm going to get an e squared over 2 times x minus 2 squared. And this seems to me to be my best possible quadratic that could ever approximate e to the x, where the center of goodness of the approximation is at x equals 2, rather than being at x equals 0. So this says we're going to be really, really, really close to e to the x when we are at the location x equals 2. The further we get away from x equals 2, the worse this estimate will be. Oh, wow. Right, and that's important right there. We are centering our estimate somewhere. We're saying we want our estimates to be best near x equals 2. We're okay with them getting a little bit worse elsewhere. So let's go ahead again and let's go pop over to Desmos and see the goodness of exactly what we just did right there. So we are looking at estimating e to the x. So there's e to the x. We just came up with this function right there. We said it's going to be e squared. And now notice, first things first, this is our best possible constant approximation of what's going on for e to the x at x equals 2, because it exactly shares that function value, right? So that's a totally sensible first term right there. It shares the function value of e to the x at x equals 2. Then we're going to add on to that e squared times x minus 2. And you should be not at all surprised to see that this is the tangent line to e to the x at x equals 2. This is exactly what that is. And then we're going to go ahead and add on e squared over 2 times x minus 2 squared. And now what we have come up with is a quadratic function that is the best possible quadratic to estimate the function e to the x if you are interested in your estimates being best near x equals 2. Far away from x equals 2, this is a pretty bad function to use to make estimates. But if you know that you're interested in evaluating this function for x values near 2, it seems like you could basically just replace e to the x with this quadratic function right here, and you're still basically going to get back essentially the same function values, right? And it looks like now we can kind of like eyeball this. It doesn't look like you got to go, even at 1, it looks like there's a pretty huge difference in value right here. Like we're off by like a whole one. Like it's like a 33% error or something like that, even only one unit away. So obviously, small order approximations are only going to have small windows in which they are good approximations. But again, we nailed it at 2. The further we get away from 2, the worse and worse our quadratic approximation becomes. But this is the best possible quadratic approximation to this exponential function centered at x equals 2 right here, which is really, really cool. And again, I really want to emphasize that you can see things like all first order Taylor series are always the tangent line to the curve that's being estimated. That's like by definition of what we're looking at with the Taylor series out here. And all zeroth order approximations are just simply the function value evaluated at where we're centered right there. So those two like super base cases right there, you should always have that stuck in your mind right there, that we're always going to get just the function value. And for the zeroth order approximation, we're always going to get the tangent line for the first order approximation out there. Always. That's always what we're going to get from our Taylor series here. All right. So super cool stuff right here that we can do these things with E. And again, we just did all sorts of representing E with polynomials, or E to the X with a polynomial, representing the irrational number E with rational integer-based fractions, stuff like that. Very, very cool. So what else can we do with power series here, or with our Taylor-Maclaurin series here? The other things that we can do is we can now finally, after I shook my fist at you guys a million times this semester, finally come up with a way that we can perhaps estimate the values of some impossible integrals. We know that this is not an integrable function, right? And I have yelled at you about this 100 times this semester. And again, as I've said every time I brought it up, I'm not saying that you don't have the skills to integrate it. I'm saying it's not integrable. It has been proven that it's not possible for there to be a closed form function that is the antiderivative of e to the negative x squared. Right? That doesn't mean we can't estimate the values of these integrals using some Taylor polynomials. So here's what I think we're going to do right here. We already found that e to the x is just straight up equal to the series n equals 0 to infinity of x to the n over n factorial. We want e to the negative x squared. And so here's what I'm going to do is I'm going to erase a bunch of stuff real quick right here and write it in different color so we can see the substitution that I'm making. I'm just going to reuse some old work here. All we're doing is just replacing negative x squared in our series representation here. And what we're going to get is we're going to get negative x squared to the n over n factorial. And that's all I needed to do right there. I now have a series representation for e to the negative x squared. If I then wanted the fourth order Taylor approximation for e to the negative x squared, let's just go ahead and find our first 4 terms of this guy right here. When n is equal to 0, we're clearly just going to get 1. When n is equal to 1, n factorial is 1, we're just going to get a negative x squared. When n is 2, it looks like we're going to get a division by 2, so I'm going to get a 1/2. It looks like I'm going to get a positive number because we're taking an even power on a negative term right there. And this is really negative x squared squared. So it's actually going to be 1/2 x to the 4th. Then our minus ones, our next term is going to be negative because we're going to take, for our third term, we're going to go ahead and get a, our third term is going to give us an odd power, so that's going to introduce the negative. We've got a 3 factorial on bottom, which is going to give us a 1/6. So I'm thinking minus 1/6 x to the 6th. And then finally, if we want to get a n equals 4 term going on out here, then that would be a 4 factorial down there. It looks like it's going to be a positive 1 over 24, and then x to the 8th right there. So this would be a 4-term Taylor polynomial. So, and I just want to say right now, I feel like the language surrounding these things always goes in several directions. One thing that is sometimes used for our phrasing is to say, find a fourth order polynomial, meaning only get your terms that go up to the fourth order term right there. Other ways we could say this are find the first four terms in the Taylor series for this approximation. Other things are evaluate your series up to n equals 4, which is actually going to get you 5 terms like we did over here. A little bit of discrepancy in the phrasing right there. Try and read those carefully. I actually probably maybe slightly like miswrote this for what I was intending. That doesn't matter. We found a estimating series right here for e to the negative x squared. And the point is that we can now use this as the integral representation then. So it now should be the case um, that the integral from 0 to 1 of e to the negative x squared dx is approximately equal to the integral from 0 to 1 of 1 minus x squared plus 1 half x to the fourth minus 1/6 x to the sixth plus 1 over 24 x to the eighth dx. Right? I just swapped out e to the negative x squared with some number of terms of its Taylor series out there, right? So I think I could say is approximately equal to then what is it? We're going to get x minus 1/3 x cubed plus 1. All right, so 5 is going to pop down, so this will be a 1/10 x to the fifth minus a 7 is going to pop down, so I'm going to get a minus 1 over 42 x to the 7 plus, and then a 9 is going to pop down, giving me 180, 216 x to the ninth. This is all evaluated and obviously shows the nicest numbers in all of human history to do math with, 0 and 1 right there. So what you can see is that evaluating at 0 and 1 means at 0 everything goes to 0. At 1, since this is a polynomial, all the x's are just 1, so we're just keeping all the coefficients. So it seems to me like the integral from 0 to 1 of e to the negative x squared dx is approximately equal to 1 minus 1/3 plus 1/10 minus 1 over 42 plus 1 over 216. And this is our approximation using the Taylor terms that we got right there. Let's go ahead and check it out in Desmos. It can do the integral for us as well. And let's see what we end up getting out here for our terms right here. So what we came up with is let's see here, 1 plus 1/3. Wait, no, sorry, hold on. That was a 1 minus 1/3 plus 1/10 minus 1 over 42 plus 1 over 216. That was our estimate for that area underneath the curve right there. What we were trying to estimate was the integral from 0 to 1 of e to the negative x squared. Oh yeah, it looks like we basically nailed it. We're accurate. The first two decimal places match. Man, if we just rounded this to 3 decimal places, it matches ours rounded to 3 decimal places right there. So it looks like this is a pretty dang accurate estimate, especially considering the fact that we know that the context in which we're interested in this is area underneath a probability distribution function is one of our biggest reasons why we care about integrating this thing. So this is like a probability. So this says what we should get is exactly a probability that you'll be between 0 and 1 standard deviations right here is this 74.68%, and we are getting 74.75% right there. So like we're nailing it right here is basically what I'm saying. Like that's a really good approximation by only using the first 5 terms of the Taylor series right there. We're getting really, really close. If you need a little bit more accuracy, it takes me literally just a few seconds to work out what the next few terms would be in this Taylor series right here. That is estimating the value of an integral that's literally not possible to do otherwise. Awesome stuff right here, right? So Taylor series are really giving us some like really, really powerful estimation techniques now is what we're seeing. But sorry, I'm going to leave this up for 1 second while I write these things down here. I'm just writing this so I can throw it in here. 4, 6, 8, 2, 4, 1. approximately equal to 0.7474867 back to Word. So I was just writing down those two numbers that we saw in Desmos right there. So this is it. I've yelled at you guys about this one like 40 times this semester, the whole e to the negative x squared, and how badly we want to be able to evaluate that integral. All we need to do is evaluate a Taylor series for the integrand, and then it becomes trivially easy to do the integration and evaluate the bounds of integration right there. So this is another way that rather than doing things like Simpson's rule for the area underneath this polynomial right here, I am guessing that this is one of those instances where it's actually easier for a computer to evaluate the Taylor series and perform polynomial integration, because that's all stuff that a computer can understand without having to go into any kind of difficult symbolic math out there, which is really, really, really cool. So this is one of our excellent applications here. So we're seeing already like kind of some crazy things right here. Estimating irrational numbers with rational series. Coming up with series that are actually straight up equal to functions like e to the x by using only polynomials, equal to over the entire real number line, which is crazy, converged everywhere. And we're seeing that we can now evaluate integrals, or at least estimate values of integrals, using Taylor series approximations, replacing the integrands that we couldn't handle in the past. And we still technically can't handle now, but we just swap it out for a polynomial. There's nothing easier to do calculus with than polynomials, right? So we put ourselves in a really good spot for that. So let's look at one other example of when this is a very practical thing that we can do right here. Oh no, sorry, we got two more examples. One, we're going to evaluate a limit. Two, we're going to solve an equation. You should see that the same limit is on the screen twice. That's because there are two different ways that we can go about evaluating this limit. If I were to just say to you, as a calculus student, evaluate the limit, then what would you do, right? And so let's look at two different ways that we could do this. One, we could replace e to the x with its Taylor series. And in this case here, I would rewrite this thing as limit as x goes to 0 of. And let's remind ourselves what that Taylor series for e to the x looked like. Taylor series for e to the x, I've got it sitting right here. 1 plus x squared over 2 factorial, x cubed over 3 factorial. Okay, I can remember that guy. Limit as x goes to 0 of 1 plus x squared over 2 plus x cubed over 6 plus x to the 4th over 24 plus dot 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 minus 1 minus x, all divided by x squared. Well, okay, so this is in one of those examples where we set things up really, 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 really nicely for ourselves. The 1 and the x are going to cancel with the 1 and the x, leaving us just with the limit as x goes to 0 of x squared over 2 plus x cubed over 6 plus x to the 4th over 24 plus dot dot dot, all divided by x squared. Now what we can see is going to happen here is that's just going to leave us with it looks like this is just going to be 1/2. X goes to 0 of 1/2 plus x over 6 plus x squared over 24 plus dot dot dot. But what you can see is going to happen is as x goes to 0, the infinite number of terms that are out here are all going to go to 0. And it looks like we're just getting 1/2 for the value of this limit right here. Now, it turns out that this was a limit that you were able to evaluate before you learned about Taylor series right here. If I were to go and do my lazy attempt at evaluation of this limit right here, I would just say to myself, okay, every time with limits, I go as lazy as I can. I say, can I just plug in that number? Can I just plug it in? Can I just plug it in? Can I just plug it in? If I try and plug in 0 right now, I'm going to get e to the 0, which is 1, minus 1, so 1 minus 1 is 0, minus 0, so still 0, divided by 0 squared. It looks like this is equal to 0 over 0, so it looks like we're going to use L'Hopital's rule. So I'm going to go ahead and say this should be equal to the limit as x goes to, because we are not only in an indeterminate form, 0 over 0 and infinity over infinity are the two cases in which L'Hopital's rule applies. So I'm going to individually take derivatives on top and bottom. When I take the derivative on the top, I just get e to the x. The minus 1 goes to 0, minus x goes to minus 1, all divided by 2x. Now I say to myself, because I'm very lazy, I'm like, can I plug it in? 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 If I plug in x equals 0, I'm going to get 1 minus 1, which is 0, divided by 2 times 0, which is 0. It looks like we're still in 0 over 0 format right here. But it seems like I could then go ahead and do L'Hopital one more time to get e to the x over 2. And as x goes to 0 here, we are just getting 1/2. E to the 0 is 1 divided by 2. So it does look like L'Hopital's rule or Taylor series approximations are both good routes to go to evaluate that limit. And part of our big lesson with this one is that what we needed here was to compare a exponential function to a polynomial function, a comparison between the numerator and the denominator. That's really, really, really hard to do because those are two different families of functions. This is this is what we would say comparing apples to oranges. It's not a like by like comparison here. By replacing e to the x with its Taylor series, we made it so that we were comparing polynomials to polynomials. We were actually able to do the algebraic simplification once we did that. So I really like to think that aside from the fact that polynomials are like the easiest family of functions to do calculus with, it's also the case that like even if they weren't, it doesn't really matter. What Taylor series are doing is they're giving us common ground to represent all functions. Every function has an associated Taylor series, may not converge everywhere like e to the x's did. It might have some narrower interval of convergence, but it still has a power series to represent it. And what that says is if you have equations that deal with all sorts of different families of functions that you could never do the algebra to get all the math to work together, you could replace everything with its Taylor series. Now everything's a polynomial, and now you get to go ahead and finally do math again, right? So let's go ahead and see that in our final example of the semester right here. Estimate the solution to this equation right here. So I want to estimate the solution to an equation, but what you hopefully can visually see immediately about this equation is it is not physically possible for you or anybody to ever solve for x. There is no solution that straight up solves for x in this case right here without an infinite number of terms. We're going to just find an estimate to the solution right here. And I don't want to go beyond the bounds of my ability to do math by hand. So I want to say, I'm kind of thinking of this as saying, if I, and I know this is a stupid thing for me to say since the year's 2021, but, I'm locked in a closet without a calculator and I got to estimate a solution to this thing with a stick in the sand. What am I going to do? To estimate this solution here. I don't want to go beyond my ability for me to do by hand math since I'm just trying to come up with an estimate anyway. And my ability to do by hand math with polynomials sort of ends at quadratics, even cubics. Like I know there is a cubic formula and the only thing I know about it is it's freaking disgusting and I never want to use it, right? So I'm thinking I just want to come up with a quadratic estimate for e to the x and flop that in there because e to the x and polynomials don't play nicely together. So if we replace e to the x with its polynomial representation, then it will then play nicely with other polynomial type terms like 3x and -1 right here. So I'm going to just kind of say what I just said right there. Let's find a quadratic estimate. So we can do the math by hand. Now, the thing I'm thinking here is this. When I say come up with an approximation for e to the x, it matters that you say, where do you want that approximation to be centered? If I thought that the solution to this equation was going to be something like 100, then it matters that I build a Taylor series centered at 100. I don't think it's going to be something like 100. In fact, I'm seeing here if I plugged in like 0 for x, then I'm getting 1 equals -1. Honestly, that's not even that far off right there. If I plugged in -1 for x, then I'm going to get -3 here and 1 over e here, which is going to be more negative than it should be. I think just by like some vague mental math, I think my answer is between like 0 and -1. And so that says to me, doing a Maclaurin series centered at x equals 0, I think is going to be a reasonable thing to do here. The solution by visual inspection seems to be a small negative number. So I think an expansion centered at 0 is okay. All right, so again, the important thing here is I'm not just using a Maclaurin series because I'm lazy. I'm saying I do think that x equals 0 is kind of close to the correct answer for this. And so centering our estimate near x equals 0 is going to give us good estimates near x equals 0. That's reasonable to me. If you were to visually look at this thing and say, I think the solution is going to be between 15 and 20 based on like just eyeballing it right here, then you should make a Taylor approximation centered at like 17. And you should use that as your polynomial that's representing your estimate of e to the x, right? So what I think I just want to do is just get a quadratic estimate centered at x equals 0. I'm going to remind myself once again what I'm looking at right here. And it looks like that means to me I'm just going to replace e to the x with 1 plus x plus 1/2 x squared. That's it. 1 plus x plus 1/2 x squared. So now I've just got a quadratic. We're just solving a quadratic. Last problem of the semester, we're just solving a quadratic by hand. Isn't that almost a little disappointing right there? So I'm going to get 1/2 x squared. It looks like that's a plus 4x, right? X and 3x. And then I've got a 1 right here. I think I'm going to add this 1 over to the other side. I want to be equal to 0 so I can use the quadratic formula. So I'm going to get a plus 2 equals 0. And then I think I'll make this the way I actually like to see my quadratics, with the a being 1. And so I go to the quadratic formula. B squared minus 4 times a times c all over 2a. So negative 8 plus or minus the square root of that's 64 minus 16 is 48 over 2. 48 is 16 times 3, so this is going to be 4 root 3 in there. So negative 4 plus or minus 2 root 3. Now, there's two solutions here. I was thinking, I think the answer is the one closer to 0. Right, like I don't think I'm getting, like, negative 6 seems like it would be way wrong to me right there, right? So I'm thinking, so we estimate that the solution to e to the x, what was it, plus 3x equals negative 1? Is x equals negative 4 plus 2 root 3. And let's go ahead and go to Desmos and see how close we are, and we'll call it a semester here. So over here in Desmos, we were interested in estimating the solution to e. So I'm going to do e to the x plus 3. That's our equation. Y equals e to the x plus 3. We want that to match with y equals 1. Oh wait, oh sorry, negative 1. Wait a minute. Oh, 3x. That's what I was doing right there. I was like, why is this not what I'm looking for right there? There we go. Equals negative 1. So, as I had done by visual inspection, yeah, I think that thing was going to be like between 0 and negative 1, like I kind of saw by visual inspection. So there's the answer that we're looking for right there. We came up with our estimate being, let me check real quick, what was our estimate? Negative 4 plus 2 root 3. Negative 4 plus 2 square root 3. Oh yeah, negative 0.53 is our estimate. Negative 0.53. Desmos won't even give me any more decimals other than that for our actual solution for this thing right here. So I am positive that we didn't nail it exactly. I am also positive that we got really damn close on this thing right here. So it looks like this can be a very good tool for estimating the solution to impossible to solve equations by converting all non-polynomial terms into their respective polynomials from the Taylor expansions, maybe even only just keeping like quadratic or cubic terms and then solving the relating polynomial equation. Remember, the important thing here was that we chose to use the Maclaurin series representation over here. We used the Maclaurin series representation because of the fact that I stopped and I looked at that thing for a minute and said, all right, if I plug in 0, what do I get? Okay, kind of close. If I plug in -1, what am I going to get? Okay, now it's too far on the other side. So I kind of did my intermediate value theorem right there to determine it was going to be between 0 and -1. So that said to me, screw it, center it at 0 then. That should be pretty close. And we did end up coming up with something that was very, very close right here. So Desmos said that this should be x is approximately equal to 0.53. And what we came up with is that this number right here is x is, what do we get? Negative 0.5359. Very, very close. Right? Right, it didn't even give me more decimals right there. I'm sure I could go ask Wolfram or something like that for more decimals on that approximation. So this Taylor-Maclaurin series idea is huge. This comes up like a billion times in math. This is like one of those tools that's like a super high powered tool, but that is also like the simplest tool. It's so simple to use. And it's really almost like a lazy man's tool. It's like every time you've got an equation, you're like, I can't solve that. Screw it. Let's just sub in the Taylor quadratics for all the terms I don't know how to deal with, and then let's just move on. That's like actually kind of okay to do. You're going to get really, really, really good estimates for all of your components if you do that. So Taylor-Maclaurin series, not bad at all to derive the formula. Not really that bad to come up with the series representations. We can often get away with just doing simple things like some algebra with the ratio test or the root test to identify intervals of convergence. We always are hopeful that our Taylor series converge everywhere for the functions, but it is definitely not the case that that's going to happen all the time. E to the x is a little bit more special like that. We will end up finding, as you're going to go like see in the homework, you're going to see when you read the textbook, other functions like sine and cosine, those also converge everywhere to their respective Taylor polynomials. Other functions like natural log of x will not converge everywhere, but you should see that things like natural log of x have a natural inconsistency with polynomials, which is that every polynomial has a domain of all real numbers, just like e to the x, just like sine and cosine of x, whereas the natural log of x has a domain of only positive integers, which makes it really, really hard for a polynomial to estimate it well when their domains don't even match between the two functions, right? So some functions we're going to end up with less than desirable intervals of convergence, meaning it's not good, it's only an estimate, not a true equality like we have in the blue box right here. And then we got to be even more careful about making sure that we're centering our estimates at good locations if we want to use a Taylor for like natural log of x. But we're seeing here that we're getting some like otherwise excellent results for many families of functions that are apparently very easily described by polynomials, which should absolutely come as a surprise to you. It's not obvious at all that we're able to write e to the x as a polynomial, but we just did. So very, very, very cool. So this wraps up our semester right here. This is the end of chapter 11 is our Taylor and Maclaurin series here. You guys are going to get another sort of like a custom Tony homework from me, similar to your polar flows assignment out there, that's going to have you walk through some Taylor stuff. You're going to come up with some Taylor polynomials for some functions. You are going to estimate some values using them. And at the end, I'm going to have you derive a very, very special formula, which is going to lead you to the formula of e to the I pi plus 1 is equal to 0 is going to be the final conclusion of your homework assignment coming up. And the way that you're going to conclude that is by way of some Euler's formula relating exponentials to sine and cosine, as well as some Taylor series stuff that's in there. So you'll get to enjoy that last homework assignment. So I'm honest to say I am sad to say that this is my last video of the semester here for you guys. Have enjoyed this, so I hope you did as well to the best of your ability. I know it was a tough semester, and yeah, I look forward to all of you guys will be taking Calc 3 and differential equations next year because it's good for you, and you should be whether your degree requires it or not. You didn't take all of this calculus just to stop now. You really didn't. So go forth into the calculus world and continue to crush it. And good luck out there. I'll be seeing all of you that come by to ask me questions about your Taylor series homework and office hours. Otherwise, have a good one, everybody.